we will make a start on our March Soils Network of Knowledge webinar. And I'd like to introduce Dr. Tavakkoli, who's one of our soils unit researchers, and he's based in Wagga. Ehsan's over 10 years experience in research and consulting in soil fertility and crop nutrition, subsoil constraints, environmental nanotechnology and soil-plant interactions. He's currently leading the New South Wales component of various national GRDC programs on improving wheat yields in sodic and dispersive soils and the amelioration of sodic and acidic soils and the understanding of crop responses to modern fertilisation techniques with a focus on improving subsoil fertility. Wow, that's a mouthful. He'll talk about some of this work today in today's webinar, ameliorating sodic-alkaline subsoils using amendment.
Thank you, Abby, and good morning to everyone who are on this webinar today. My name is Tavakkoli, as Abby introduced me already. So what I'm going to talk about today is some recent results from the work that we are doing with amelioration of subsoil constraints. And in the first couple of slides, I will just talk about the basics, that what is a salt-affected soils, what make a soil sodic, what is salinity, and then explain actually the actual research that we are doing and the plan for the future. Before I go ahead, I would like to acknowledge and thanks all the co-authors of this presentation and the people behind this work, a number of different people from different organizations, but mainly the soils unit in DPI New South Wales contributed towards this work, that without their contribution, we wouldn't have any results. So to start with, as you can see in this slide, it's very important to be able to recognize what is a salt-affected soil and then different issues that happening from different sources of salinity. What I like to say here is that if you have a clay particle, that clay particle carries a negative charge, and that negative charge attracts different cations, elements with a positive charge, and distribution of that positive charge around the clay particle is basically create that cation exchange capacity. And if you look at these different circles here, calcium, sodium, potassium, magnesium, you will see there are different sizes of these circles. That means the larger elements, for example, for calcium, which is a divalent cation, compared to sodium, which is monovalent. If this distribution is in favor of one or two of these elements instead of having an even distribution, what happens is that your chemistry of the soil is going to be affected by that. So if you have too much sodium in that soil, instead of having a better contribution from potassium, magnesium, and calcium, the soil becomes sodic. Why? Because the relative amount of that sodium compared to calcium is too much. And this is just the simplest way that we can talk about why a soil is becoming sodic. The problem with the use of terminology of sodicity is that although sodium is the main element that causes that dispersion and that problem on sodic soils, however, if you have quite a lot of the other cations, such as potassium or even magnesium, instead of having enough calcium in that soil, you will still see some effect of those other cations in making in the soil to become sodic or magnesic or dispersive. So it's very important to identify, and the identification at the field level will only comes up if you're doing a proper deep soil testing and having an idea of what is the soil pH, what is that calcium and magnesium ratio, and what is the amount of sodium and potassium on the soil. So too much sodium, let's keep it simple, cause dispersion. On the Petri dish on the right hand side, again, it's very important to be able to distinguish between dispersion and other behavior of the soil, such as slaking. So dispersion is very different from slaking, and if you have dispersion at the field level, as you can see at the bottom of this slide, we often get if it happens in the soil surface, we get a dispersive clay on the soil surface. And as it dries down, it actually becomes really, really hard and cause a few problems. The germination of the crop will be affected, and also we get a massive infiltration issue of the water, and we experience waterlogging at the field level. So the fine particle of that soil in this Petri dish, if you just visualize that at the field level, those really, really fine particles, when the soil is dispersed, can move vertically and horizontally in the soil with the water and clog all the pores. And when the pores in the soil is being clogged, then the waterlogging happens. And this dispersion can happen across the whole soil profile, from the surface to the subsoil. And how the soil becomes sodic? So both salinity and sodicity, there is one problem in common. There is too much salt in that soil. However, over maybe 20 years or 1,000 years, as a consequence of irrigation or rainfall, that salinity leached down to the deeper soil profile, and it leaves behind some sodium, and that sodium can be attached to the clay, as I explained in the previous slide. So in salinity, on the left-hand side, you have a lot of soluble salt in the soil solution. It's not a part of the clay, but it is a part of your soil solution that whenever the water hits the soil, that salinity becomes soluble, and on its own, you have a saline soil that the plant will experience some sort of stress. Over that many years, that if you are in an irrigation system, it's much faster. If it's in a dryland farming system, it takes years and years to come to create a sodicity issue. That sodium chloride goes down, but by calcium will leach down, but still that some sodium remains attached to the clay and make the soil sodic. So that salt affected soil is the reason for the interplay between salinity and sodicity. Depends on the soil type, depends on the amount of rainfall and the environment. However, there are quite a lot of scope for ameliorating these soils. So traditionally, for a sodic soil, and from now on in this presentation, I'm going to focus on sodic soil instead of saline soil. Gypsum has been always a common practice because gypsum is a rich source of calcium, and that calcium can exchange with sodium. It has been shown that if we add gypsum to the soil, we get a response from the sodic soil. But in reality, if you look at the soil profile from the surface to the subsoil, the amount of gypsum that often needs to be added into the soil is something about 20 or 30 tons per hectare to ameliorate the subsoil that's suffering from sodicity. Some new technology has been introduced in the past few years, and one of them is subsoil manuring, and this is an example of the work that Peter Sale did in the high rainfall area of Victoria, where transformation of that subsoil structure after 3 or 4 years of subsoil manuring was evident. And on the left-hand side, again, you see a control soil that it's like a farmer practice. And on the right-hand side, a very well-structured soil after that subsoil manuring. And those changes in soil structure was associated with up to 70% yield increase. So this is really exciting, but there are a number of barriers in terms of adopting this sort of technology. One of them is that although we observe this sort of transformation in some of the areas in farming system, it's something that we cannot predict that happens everywhere. So our inability to predict where the response will occur is a bottleneck in adopting this subsoil manuring or subsoil amendment work. The other thing is that it's a very expensive task to do. So to be able to make sure the investment, a great investment using subsoil manuring, is going to pay back, we need to be able to make sure if we add so much amendments in the subsoil, is going to give us that response. So different environment, different farming system has different constraints. So I talked about sodicity, salinity, the low pH on its own or acidity is a problem. Waterlogging, which is related to acidic soil, also a problem. And you have these problems in dryland farming system or irrigated systems. Across all these problems, there is something in common between all these different constraints, and that is poor water use efficiency. That means we have quite a lot of water in the subsoil, for example. However, due to those physical chemical constraints or maybe a nutritional constraint, we cannot effectively use that water in the subsoil, and therefore we have a reduction in the yield, and profitability also decline. So this is on the left hand side, this is a yield gap map of the Australia. This is the work that has been done by modeling by CSIRO scientists, and what is actually showing is that across the width V belt of Australian farming system, from the Western Australia to the south and east, there is a quite a significant yield gap from what we can actually achieve and what we are getting at the moment. And it's anything from just under 1 tons per hectare to about 2.4 tons per hectare. If you compare that map on the left-hand side with the map on the right-hand side that represent the distribution of sodic soil in the farming systems or in the soils across Australia, you will see that often those areas that suffer from that yield gap is also dominated by soils that have some sort of constraint. In this case, I'm just showing the Sodicity. The argument is that, again, the management of subsoil constraints could effectively contribute to close that yield gap. If you think about the effective use of water and you have a constraint that prevent the water to be used by the crop, that management or improvement in the system on its own is quite a significant achievement if we can do something with it. And a back of envelope calculation, an extra 10 mils of water in the subsoil in a very critical time, adventices, or in the spring where the crop is flowering or grain filling, if we make 10 mils of that unavailable water available to the crop, that on its own is about an extra 0.6 tons per hectare of extra grain yield. So to investigate what are the potential for ameliorating of subsoil constraint, we conducted a number of trials. This is a part of a larger project that is led by Professor Armstrong from Victorian Agriculture. And we have 9 of these sites, and I'm going to talk about the Southern New South Wales experience. And in this slide, we just spend a few minutes to talk about the soil characteristics. That's what we are dealing with in this property. The first thing that I'd like to highlight is the pH, and we measure the pH in water. And I'll explain why I'm emphasizing on water versus calcium chloride. Most of the soils in the southern region of Australia have a pH of about between 5 or 6 in the topsoil, and the pH increase massively by depths. And in deeper profile, we actually reach a pH of about 8.5 to 9. So a lot of soil tests, if you look at them, they are reporting pH in calcium chloride. That means although that pH in calcium chloride is really good for acidic soil, because it shows that reality, for the alkaline soils in deeper profile, if we use a calcium chloride solution to measure the pH in, the increase in calcium chloride and calcium carbonate from the soil gives us a saturation effect in the solution, and the reality of the pH of 9 is not being represented, and the pH always come back as something about 8, 8.1, because a saturated solution of calcium chloride doesn't exceed pH 8, 8.1. So it's important to measure the soil profile pH in water if we have an alkaline soils. And at that pH of about 9, we have toxicities of carbonate and bicarbonate species of different salts. Sodium carbonate, for example, is one typical example. And the pH, the high pH on its own, create dispersion on the clay surface, which I will explain why. So in terms of pH, we have an okay topsoil with a pH of between 5 and 6 or 7, and then it reached about 9 at below 40-50 centimeter. In terms of salinity, the EC, again, most of the soil that I've seen in the southern region have a non-saline topsoil, and then the threshold for salinity being 4, we observed that salinity to start or kick in at about 30-40, sometimes even deeper profile, 60-70 centimeters. So in most of the cases, we have a subsoil salinity below that 50-60 centimeters. Again, salinity on its own creates osmotic stress for the crop, because too much salt means that the water cannot be taken up by the plant properly. And then we talk about ESP. ESP is our indication of how much exchangeable sodium is in the clay. And if we have more than 6% of exchangeable sodium, the soil is become sodic. And if that increase beyond 10%, it's actually really, really sodic, and dispersion and waterlogging often happens. So it's a very similar trend to the pH. We have often a non-sodic topsoil, and that sodicity increases with depth. In fact, the reason for the soils to become sodic, one reason for that is the high pH in the subsoil. If you have a lot of sodium carbonate, sodium bicarbonate, the sodium of that sodium carbonate salt remains on the clay and makes the soil sodic. And if you see the Petri dish tests at the bottom of that graph, you will see a gradient of dispersion from topsoil to the subsoil. So again, the topsoil usually is not really dispersive, but that dispersion increases with increasing depths. And on its own, dispersion is a problem, as I explained, in terms of waterlogging or reducing the infiltration or affecting the crop germination. So in this system, in one property, in one farm, we have quite a few issues. And instead of just talking about sodicity, we are dealing with a soil that has a high pH. In the subsoil, it's saline, and of course, it's also sodic. So that's why I call it an alkaline sodic soil. And any strategy to manage these soils should be able to address 2 or 3 of these different stresses together instead of just one. We choose a number of different amendments to look at this capacity or potential of these amendments to ameliorate a treatment, and I categorize them to inorganic and organic treatments, and these treatments being either applied at the soil surface or being placed in the subsoil. And to place these amendments, some of these amendments in the subsoil, we used a machinery that is built and designed with New South Wales DPI. We call it a 3D ripper. So we have a dual depth delivery of amendments that could be an organic amendments or a gypsum or lime and liquid fertilizer on their own or simultaneously. And we can achieve a depth of about 40 centimeters to place these amendments in. Coming back to the amendment on the left-hand side, so I just briefly talk about what do we have here. We have gypsum, of course, because it's a common amendments in many amelioration of sodic soil practices. We use liquid nutrient, which is NPK, and we use that to see if some of the other organic amendments that we are using, are they going to provide us anything beyond the nutritional effect of the amendment on its own, because some of the manure is, for example, rich in nitrogen, or can we actually get a plant response just from putting a nutrient on its own in the subsoil? We used chicken manure. We use some of the farm-grown biomass as well. So PS row here is basically a field pea hay being pelletized. We used it on its own, or we incorporated gypsum and nutrients into that pellet, and we have, for example, a treatment that contains the organic matter, contains gypsum, contains nutrients. And of course, we had also a rip-only treatment to compare to see what is just the ripping only doing in relation to or relative to some of these other amendments. So this is This is an aerial photo of the trial in RAND. So 15 treatments with 4 replicates gives us about 60 plots. And the trial was set up in 2017, and we will monitor the changes in crop response, soil chemistry, physics, and biology over the next 4 or 5 years to see what happens to the soil and the crop across these different treatments on the RIP line and off the RIP line. Okay. So the most important thing that farmers and agricultural consultants ask is the yield. What is the yield response of the crop? So let's talk about the yield first. And in here, this is the result from 2018, which was an incredibly dry season. We had a wheat crop variety Lanza, and on the y-axis is the wheat grain per tons per hectare. And first of all, I just compare the control versus RIP only. Our control was also very similar to the farmer practice, something about just below 2 tons per hectare, about 1.6 actually. And RIP only, if we don't have any compaction in the system, if you just rip the soil, because of that disturbance in the soil physical structure, we often get a negative response in terms of yield penalty. So that wasn't something surprising. We often experience that. Then some of the treatments that didn't really work well in relative to the control, there were most of the surface amendments, so surface gypsum, surface manure, surface pH being pelletized, and also when we put the deep nutrient. So just to avoid any confusion, this is the second year of the result for an amendment that has been incorporated in 2017. So this is the second crop on that. So some of these surface treatments didn't really do well, and they were either similar or worse than the control, right? And then we had a number of treatments that performed really well or well enough. And most of those amendments that we put them in the deep soil actually provided some significant differences. One of the treatment, which is on the right-hand side, a combination of deep pH plus gypsum plus nutrient, performed remarkably in both years, 2017 and 2018. And we have a working hypothesis that why we get such a good response from this treatment. Altogether, if you compare across treatments, compared to control and the farmer practice, we were able to increase the yield by 53% in that deep pH plus gypsum plus nutrient. There were some other responses, for example, from deep gypsum and deep pH by about 30%. So the results are quite encouraging that some of these treatments have quite a remarkable ability to improve the yield. Going backward, in 2017, we had a barley crop, variety Latrobe, and very quickly, because of the time, I'm just going to highlight the consistency of that deep pH plus gypsum plus nutrient, that we got about 27% increase in terms of yield response relative to control. Deep manure performed well in 2017. However, it moved to the left-hand side a little bit and lost that potential a little bit. It still is better than control, but it didn't perform as well as we wanted. The deep pH, if you compare again with 2018, that also provided quite a good result in both 2017 and 2018. So I categorized them to top performing treatments. Deep pH plus DP plus gypsum plus nutrient performed well. So in that a slide where I explain the soil characteristic, that we have a pH, we have also EC problem, and we have salinity, and we have sodicity problem. I also mentioned that we have a multiple soil constraint. So it's not just one problem that we are dealing with. And the treatment that we designed here, including the organic matter in form of plant-grown, farm-grown biomass, deep pH, and gypsum and nutrient, included all these treatment to provide different mode of action. So deep P pellet is full of carbon, so it's 40% carbon in that plant biomass that can be used for aggregation of a poorly structured subsoils when we have sodicity. Gypsum on its own can interact with exchangeable sodium on the clay, provide a bit of a structural benefit. More importantly, that people often talk about it less, when you add gypsum into a sodic alkaline soil, it actually reduces the soil pH significantly, and I will show you in the next few slides. And that nutrient incorporation into that pellet also boosts up fertility of that subsoil, even if it is just for 1 year or 2. The DP on its own still is a good amendment, because compared to some of the other organic amendment that is rich in carbon, we also have about 3% nitrogen in DP, and that carbon to nitrogen ratio, when you deep place an amendment, it's important for triggering the microbial activity in the subsoil that can use this carbon, and that microbial carbon can be used for aggregation of the subsoil. The next slide talk about some of the interesting results, and these are the amendments that performed less exciting in 2017, but in 2018 they showed quite a lot of potential. And there are 3 of these amendments. So deep wheat stubble on its own or plus nutrient didn't do much in the first year, about 5 or 10% increase, but in the second year we actually achieved about 20-25% increase. And the reason behind that, in my opinion, is that wheat stubble or any cereal stubble is really high in carbon, low in nitrogen. So basically you put it in the soil and it takes much longer for the microbes to be able to break this down, and that organic carbon fraction of these amendment to be useful for any aggregation. The deep gypsum on the right hand side again didn't work really well in the first year. In the second year showed some remarkable result. Gypsum needs to react with the water either in the surface or in the subsoil, and that reaction is slow, and the solubility of gypsum, even though it's much more than lime, but still it's a low soluble salt, so it takes time to dissolve and get a benefit from a gypsum that being incorporated, and not seeing some effect in the first year and seeing some effect in the second year is important. So these are really interesting treatments, because in terms of cost effectiveness, these are much more cost effective compared to a manure or any other combination of them to make it which makes it more and more expensive in the future. This photo is just an example of the 2018 plots, and basically on the 25th of September 2018 I visited this site. On the left hand side you will see an ameliorated plot, and on the right hand side a control plot, and also the whole paddock, which was farmers practice, was similar to this. Severely affected by drought and also a few frost, and availability of the water in the subsoil is very important for crop to tolerate those abiotic stresses such as drought and frost events. And in my opinion, again, what happens in terms of water uptake of the crop affected by an improvement in soil structure under some of those treatments led the plant to be able to get more water from the subsoil, and basically having a much more vigor and health. And we showed that by measuring the water uptake at different depths. So this is the result of using neutron probe to detect how much water is in the profile. And I didn't actually convert it to the volumetric water content, but basically, if you move to the left-hand side of this graph, there is less water in the soil. So that means more water has been taken up by the plant and less water has been left into the soil. And the graph that is on this slide is the control treatment. So that's the pattern of the water uptake at antithesis by the wheat crop. And if you look at another treatment that in terms of yield response didn't really work, it's very similar to the control treatment. So this is deep NPK that we added. There is always a bit of water used in the surface, but in the deeper soil profile, we see there is not much changes. If we look at our deep P, gypsum, and nutrient treatment, and compare that to deep pH on the blue, with the blue line, you will see that there is a gap between the control treatment and these other treatments in terms of water uptake or the pattern. And if you do pull the data together across that soil profile, in average, there has been an extra 10 or 15% of the water uptake being used by the crop under those treatments. That means the water that was stored in the subsoil became available to the plant to be taken up, and that contribute, of course, to the grain yield and grain response. In this slide, I want to summarize some of the mechanisms associated with amelioration of subsoil constraint. So I talked about pH, I talked about ESP, and I talked about aggregation. When we have, and this is the work that Yuning Fing at New South Wales DPI in Sydney done for us, and it's a remarkable story because it simplifies the interaction of these different amendments. Basically, in terms of pH, if you have an alkaline sodic soil that we had in southern New South Wales, the control treatment is about just 8.8 or 9, and as soon as you add gypsum into that soil, that pH reduced to about 8 or 7.8. So it's a reversible mechanism, so the pH often stabilizes at about 8.2, 8.3. But it never goes back to where it was at the first place. So reduction in that pH, a significant reduction from about 9 to 8.2, 8.3 was achieved by adding gypsum. When you add organic matter, and Yuning in here added plant biomass, the reduction in pH was a little bit and nothing remarkable to change that speciation of sodium carbonate and sodium bicarbonate to the lower pH where we can see calcium carbonate. So that's what I forgot to say. There's a lot of sodium carbonate in that pH 9. There's a lot of calcium carbonate in that pH 8.1, 8.2, and that's where we want to be. So organic matter or organic matter plus nutrient doesn't have any influence on the pH, or very little. It's the gypsum effect on the pH. In terms of looking at the ESP, if you add gypsum into the soil, and we added only 5 tons per hectare in this case, the ESP reduced from about 12.5% to about 10.5%. So although it's 2.5% reduction, but we still have quite a lot of sodicity left in the system. So gypsum and gypsum plus organic matter achieve that, but it is only the gypsum effect that affect the ESP. So organic matter on its own has very little influence on ESP. And the major influence that we achieved here is by gypsum effect on the pH so far. And if we look at the microbial biomass carbon, so microbial biomass carbon that was calculated, and I just want to simplify that, it's the carbon in that amendments that we need to build up aggregation, or over time that microbial biomass carbon is going to help us to achieve that aggregation in the subsoil. The control treatment and gypsum has very low quantity of that microbial biomass carbon. Because it's a biological mechanism, as soon as you put organic matter or organic matter plus nutrient, the microbial activity increases, because organic matter is a source of carbon and nutrient, and basically we build up that microbial biomass carbon. So the effect of organic matter is mainly on building up that carbon for aggregation to act as a binding agent. Okay, so to put all these mechanisms together, a reduction in pH by gypsum, a little bit of reduction by in the ESP by gypsum, and a massive increase in microbial biomass carbon. When you look at the soil structure affected by these different mechanisms, we will see that in terms of any improvement in the soil structure by amendments, there is a bit of response to gypsum. It's a significant gypsum, significant increase compared to control. There is a little bit of extra aggregation compared to control achieved by organic matter. And when you add these together, I want you to remember our best result in the field was when we put a pellet that contained organic matter, gypsum, and nutrient. So in this case, when we put them together, there is an additive effect, and there is up to 4-fold increase in soil structure. And what Yuning done here, this observation is after 90 days of incubation, and we detect the same things in the soil in the field after about a year of adding those amendments, that we can build up or improve that soil structure or soil aggregation by combination of organic matter and gypsum. And it only achieved because we are reducing the pH, which is one problem, and also ESP, but also adding carbon to the soil that is building up that structure. So a multiple soil constraint is being actually ameliorated, and that's why that additive effect is there. So in summary, if I want to put everything together, the outcome of the work so far over 2 years is that the deep placement of some of the organic amendments with gypsum and nutrients significantly increase the yield, and the mechanisms is a reduction in net dispersive charge and pH, and the second mechanism is enhanced microbial biomass carbon, and when you have them together, it's an additive effect to give us about 4-fold enhancement in aggregation. And it's very important to put together these in context of soil water use, or sorry, crop water use in the subsoil. So at the field level, in the second year, we were able to demonstrate that the increase in plant available water and addressing that yield gap that I talked about at the beginning. So I also want to acknowledge a number of different organizations that are involved as a part of the bigger project that I mentioned, and leave you with a message here. So this is a remarkable work by one of my colleagues in Canada, Cynthia. She basically, if I want to simplify this, we were discussing about soil aggregation and how we can actually create a soil, and she decided to set up a large experiment, and she converted a sand on the left-hand side to a soil on the right-hand side after 15 months. And what she did, she added water and organic amendments that she designed, those model compounds, a pectin or cellulose, and every month or every couple of months, she added that to that soil, to that sand that had no life in it, and actually turned that sand into the soil. So the message here is that if you want to develop a better structure, a better place in the soil for the crop to live in, we can actually do that. If we think about what happened, what was achieved here by development of the soil, an artificial soil based on organic matter chemistry, and also the work that I showed from Peter Sale, that how we transformed the subsoil clay after 4 or 5 years by subsoil amendment. The message is very clear that manipulation of the subsoil is possible, but it has to be tailored to an environment where the problem is and understand what the problem is. And thank you very much.
Thank you, San. That was a really useful update on the issue and also your work, and obviously clear indication that the whole is greater than the sum of its parts. So now, as I said before, we have time for questions. Luke, who's in Dubbo, may have a question for you, Ehsan.
Thank you, Ehsan. I hope you can hear me. I've got one question for you. First of all, thanks for a great talk. I know there's huge interest around New South Wales and Queensland and probably the rest of Australia in this topic, and there's just so much to it. But one little thing that I'd like to ask is, can you explain the interaction between high pH and sodicity?
Sure. Thank you very much, Luke. So this is an area that, as I mentioned in my presentation, often being overlooked in the sodicity and salinity science. So for a soil to become sodic, you need to have sodium species, and salt in the soil is not just at the form of sodium chloride. Actually, we have a lot of sodium carbonate, sodium bicarbonate, and potassium carbonate. A combination of all these salts in the soil not only contribute to the salinity and sodicity, they also contribute to the pH of the soil. So as I said, if you get a soil just with calcium chloride, the pH is about 8. However, if you have a soil with some other species such as sodium carbonate and bicarbonate, the pH reach about 9, and this is a very, very widespread situation across most of the subsoils in Australia. And the pH and carbonate relationship is a speciation, it's a thermodynamic equilibrium. That what happens if you change the pH from 9 to 8, the form of that carbonate in the soil is going to change as well. So the solubility of sodium and sodium bicarbonate and carbonate will shift back on that diagram, and you will have a domination of calcium carbonate. So when you have high pH, you have a lot of high negative charge, and that negativity has a repulsive charge on the clay, which causes dispersion. If we can reduce that pH, we will be able to also reduce that dispersion of a sodic soil, because we are changing the contribution of those carbonate bicarbonate species.
Great, thank you. This is very complex. We've got lots of good questions now, and I'll start at the top. Steve Kimbers asked a question that kind of occurred to me too. He was asking about the costs and the balance of the costs associated with the techniques that you're talking about. Is the cost greater for the application of the product? Is the application or the product the bigger cost? Sorry.
Okay. It's a very good question, and I think at the end of the day, the only way that this work at the field level is going to be successful, if it shows up some success, is how cost effective it is. The greatest cost at the moment is the amendment itself and the freight of that amendment to the property. So if we just focus about manure, so there is not enough manure in the system. Some farms are really close to the manure, but if a farmer has to freight some manure from off the farm to the farm, that freight cost is the killer. But it's a very complex economical analysis. At the end of the day, it's a one-off amendment application, and it is the residual effect of that application in terms of the crop response over 5, 7, or 10 years that is going to give us the indication whether this is cost effective or not. And there are a number of evidence at the moment from the work that Peter Sale did, from the work that has been done in the high rainfall area of Victoria, and also in this project, we have a component where we are monitoring the existing subsoil amelioration projects that has been done in Australia over 10 years. And when you look at those sites, after 10 years of monitoring those sites, in some of those, there is a still 60–50% response of the crop to that amendment application 10 years ago. So we can only talk about cost effectiveness when we build up data in terms of crop response and the changes in the soil after 4 or 5 years. And we have an economist on the project who is capturing all these data, build up a model, and in that model there are other factors about, for example, if it's a pH problem, if it's acidity problem, what is the cost of that acidification to the price of that land? Because acidification never stops. So amendment, what we are trying to achieve in this project, can we design a cost-effective amendment? Of course, gypsum, if we have a source of gypsum that is going to work in the subsoil, it could be one of the cheapest options. Can we use just an agricultural waste, for example, a farm-grown biomass, pelletize it and put it back into the subsoil? Those sort of options are the cheapest options and most cost effective. So basically, yeah. So it's a range of different things from farm-grown biomass, and how simply we can basically convert these cheap, unnecessary items in the field to something valuable that can give us that option. And the example that I talked about, interesting treatments, which was with a stubble being pelletized or gypsum being incorporated in the subsoil, are two examples of those two amendments.
Yeah, I think it's a good point, and I think it'll be really interesting to see how that longevity stuff plays out too. I think that would be really interesting. Okay, so thank you for that answer. There's a few questions around the amendments, which I'll try and incorporate a few things. So there was one about how deep the amendments were placed. So you want to answer that one?
Sure. With the machinery that we have access at the moment, the deepest we can do the deep ripping is about 40 centimeters, and the row spacing on the ripper machine is about 50 centimeter. And there are 10 rip line per plot. So if you have a plot of 2.5 meter, you have 10 rip lines. Each rip line reaches about 35 to 40 centimeters, depends on how clay content is going to let us to do the ripping.
Okay, great. So, and then there was one about how you determine the rates of manure at that 8 tonne per hectare.
Yeah, sure. The work that I referred to by Peter Sale and a few other people in high rainfall Victoria, they used about 20 tons per hectare, and that is fine because at a high rainfall environment, we can actually do up to 20 tons per hectare. And why they choose that rate comes back to the capacity of that machinery. That is the maximum capacity of application of 20 tons per hectare. In southern New South Wales, where it is a medium to lower rainfall area, if I put 20 tons per hectare, it actually going to burn the crop because the manure has a very high nitrogen content and too much nitrogen in the subsoil. You get a lot of vegetative response, but the crop will hay off during later on the season, and that massive vegetative response doesn't often relate to grain yield response. So reducing that 20 tons up to 8 or 10 tons per hectare was decided based on the calculation that we did, that how much nitrogen we can actually safely put in the soil without affecting the crop, and that was a very good strategy. Otherwise, I have seen some results from other projects where they put 15 or 20 in a medium rainfall zone, and they didn't actually get that grain yield response.
Yeah, that's a good point too. Okay, so kind of following on from that, Amanda's asked about what the best way to incorporate the organic matter at rates needed to improve soil structure. So you sort of touched on that a bit.
What is the best way to incorporate the
organic matter at the rates that you need to improve soil structure?
If there's a little bit of further explanation, that would be good.
Right,
but
I'll ask her.
From what I can,
for a farmer.
I think, is that what? Yeah.
Yeah. So a lot of farmers that I've worked with, basically they just do a surface application, right? A surface application of organic matter, although it gives some initial response, which is mainly nutritional responses, and also some carbon for the topsoil. If you think about this presentation and the wider problem, most of that problem that I talk about is in the subsoil. It's below 20-30 centimeter, and any beneficial effect of that organic matter in the topsoil is not going to reach down to that subsoil profile. Although it's good to put it in the topsoil for the sake of just that crop establishment over years and years, that subsoil still remains a hostile condition. That's one thing. The other thing is that the maximum or the most activity of microbial community is in that top 5-10 centimeters. That means the organic matter that you put in the topsoil is going to be used by microbial, and it will be decomposed very, very quickly. And we saw that in many trials. However, if you place that in the subsoil, that means there is a slower microbial activity. That oxidation of organic amendments is slower, and you will have a slow release carbon. And again, I'm talking about that wheat stubble that we put it in the subsoil. It took us 2 years to see some effect in terms of aggregation. Is actually talking about that, preventing the organic matter to be lost in the surface soil by oxidation and high microbial activity, actually doing a favor to that amendments to stay active for longer time.
Yeah, that's a good point.
And for the farmer, by the way, so machinery is still, we are at a very early stage of developing machinery. The machinery that we have access to is for research purposes, so it's not going to be commercial. But I know several farmers who build custom built machine, put a hopper on a deep ripper to be able to do this organic matter injection or gypsum or lime injection into the deeper soil profile. And I think it's something that we will hear quite a lot about it in the next few years.
Yeah, that's great to see that some people are starting to do it, and I guess that ties in with the economics of it as well, which we'll know further down the track. Yeah. There's a question here from Corinne who wanted to know whether the responses that you were seeing, how did you determine whether the responses you were seeing were not just a nutrient response? Because she's asked, can you clarify, did all the nutrient, i.e. the NPK treatments, only supply the equivalent to the 80 kg per hectare of DAP? Yes. So that
sure.
You know that it's...
No, actually, that's right. That slide that I put about the rate of application, we actually corrected that rate of nutrient application. The amount of nitrogen and phosphorus we put in the subsoil is equal to the nitrogen and phosphorus concentration of manure at that 8 tons per hectare. And in the second experiment that we have in another site, that is also the case, but we have a low and a high nutrient amendments. In terms of and what I think the message that I would like to emphasize here, it's a system, it's a package. So I'm not ruling out there is a nutrition effect here. Definitely there is, but also we are observing a significant improvement in soil structure in the field and in the incubation experiments. Okay, so the wet aggregate stability is a very, very reliable measure of your soil structural responses. We also observe a water use pattern being changed by the crop. Again, that water change pattern only changes in most of the cases when you make the water in the subsoil available to the crop. And we also observe reduction in pH and and ESP in the field and in the incubation experiment. So when you put them together, it's a package that can resolve a few issues at the same time. Most of the soil in Australia in the subsoil has a very poor fertility in the subsoil, poor structure, poor chemical, deficiency of chemical or toxicity of some of the chemicals. So tackling all these issues at the same time and measuring all these parameters at the same time will provide a functional characterization of the system that the plant can, we can explain the crop response to that. So in my opinion, it's certainly beyond just a simple nutritional response, although it's one component of a bigger picture.
Good answer. Yeah, I think it's important to remember that it's everything together. I hope that answered the question, Corinne. Just let us know if it didn't. Andrew's asked, is it worth trying organic matter plus elemental sulfur on alkaline soils? Do you want to comment on that?
Yeah, that's a very good question. So theoretically, yes, it's a good thing. And I included that treatment in our second 2018 field experiments, which we haven't got any crop data yet. But elemental sulfur, theoretically, when you put it in the soil, it reacts with the water and it reduces the pH of the subsoil. And when you have organic matter there as well, so you also add that microbial biomass carbon. I'm really looking forward to see what's going to happen in that treatment in the future in the field. The oxidation of sulfur is slow, which is good because that means the pH will gradually reduce if it works. And we can also add sulfur oxidizing bacteria. There are inoculum in the market for that to speed up that process. But elemental sulfur, in my opinion, has some application in the future in high pH soils. But again, when you talk about high pH, it has to be a pH of about 8.8 or 9 to start thinking about ameliorating that pH. If it is below that 8.5, probably it's already okay. You cannot achieve further in terms of getting a response from the crop.
Okay, great. So that I hope also that sort of goes to answer some of the a question that Julian White also had about sulfur and gypsum. If not, just let us know, Julian. Ben McTaggart's asked about what depth the samples, I take it he means, were taken for the chemistry stuff around pH, ESP, microbial activity, that sort of thing.
Sure. So when we are setting up the experiment, we know by the help of GPS and a number of things, we know where the rip line is exactly, each of the rip lines on the plot. And what we do, we go back every year and we do soil sampling for physics, biology. So on the rip line and off the rip line, we are taking samples from 0 to 10, 10 to 20, 20 to 40, and 40 to 60. We're actually going deeper, but so far we just focused on these samples for analysis. That covers the sample or the soil above that amended layer and immediately below that amended layer. And by monitoring this over the time, we can detect any changes beyond that amended layer horizontally. By taking samples off the rip line, we are hoping to be able to detect that amelioration, if there is any response beyond that rip line, into the right or left vertical side of that rip line that can happen. So all the sample is taken from that area, and the same sample is being analyzed for chemistry, physics, biology, to find what is that mechanism and what is the response.
Yeah, so you're looking vertically as well as horizontally from the application point.
Correct. Yes.
Yeah. Okay. James Hawkins has asked, do you see the potential for SSA in pasture systems working economically for increasing biomass for increased fodder production?
It's a good question, which I'm not sure I can answer this. So definitely there is potential. Definitely there are quite a lot of constraints in pasture production. And again, we need to recognize and identify what the problem is. And I think in pasture production, a lot of issues is associated with acidity.
Yeah.
And that's a completely different situation. So you still have subsoil acidity, or there might be an example of having subsoil acidity and the deeper profile has subsoil sodicity, but that acidification in the pasture environment, I think, is a bigger problem. And looking after that, yes, definitely there is a potential there. And
the economics we won't know until we know further down the line, like you were saying.
Yes, the economic is a long-term response, and the economics needs to be based on that long-term response.
Steve Kimber made an interesting comment further to his comment about the economics at the beginning, and he said he was also thinking that the draft required for reapplication, if indeed that's needed, would decrease with time if you've got improved structure and things like that, which is a good point.
Yes, that is a very good point. And so by monitoring the changes over 5 or 10 years, we know where some of these treatments are going towards. And the rip line already is there, although it can close back again to where it was a little bit. But and putting the amendment back into that rip line for further amelioration doesn't need to be another complete application of treatment. It could be just a fertility boost that we just go there and inject nutrient, for example, and for the remaining organic matter to be used by the microbial activity for building up the microbial biomass carbon. But it's such a complex area that unless we have all that information over time, answering some of that is just a little bit descriptive at the moment.
Promil's asked if you consider about today's farming approach, which is a sort of strategic approach, what's the monitoring time period you recommend to farmers for the reapplication of the treatment, and how can we set the rate of amendments needed while comparing the grain yield over the years? It's a big question.
That's a big question. So I think that first part of the question, not anyone can answer that. We cannot yet identify how many years we can monitor, and that's something that we just have to observe over time. So there is no black and white answer on that. The second part of the question, how we decide about the rate of application. In this project, what we did is that we listed what sort of amendments has the potential to go into the field and their different rate of studies. And then when you set up something like that, you need to have replicates. It's something like a few hundreds or thousands of plots that we need to do in the field. To do that in the field is impossible because the budget and the magnitude of the work is so high. We often do that sort of work in the glasshouse. So we bring the field into the glasshouse, either by doing intact soil cores or just soil coring, setting up pot trials and having a few hundred of those pots with different rates of different amendments, and put a critical level of, for example, how many tons of amendment of manure provided the best response, and even those data at some stage could be modeled and predict. So some of the glasshouse work, controlled environment studies that we've done is going to be very useful in setting up the rate of application that we need to do in the field. And that was the first part of the project in the first year that we ran a number of those trials. And one of the deciding factors for the rate of application in the field came from those studies.
Yeah, I think that's a good point. You have to do these things in the right order before you get to that point. Just another point of clarification from Corinne. So she said, does that mean that what you said on the slide is not right, that it's not the equivalent of...
No, so the rate of nitrogen and phosphorus that has been added to the soil is equal to the amount of nitrogen and phosphorus that was added at 8 tons per hectares of manure. So what is saying in the slide at 80 kilogram per hectares of DAP is incorrect. You are right.
Yeah. So what you're saying is that you've got the amount and the manure and you've equated everything back to that. Yeah.
So by memory, I think it's about 250 units of nitrogen added into the subsoil.
Okay.
Yeah.
All right. So we're at our hour now. So there doesn't seem to be anything else. I hope that I covered off on everyone's questions. The project is ongoing, like you say, for a couple more years, and we'll watch with interest about what happens.
Absolutely. Thank you.
Okay. So thank you very much, Ehsan. It was really interesting. And thank you for participating in today's Soils Network of Knowledge webinar. Remember the other community of interest tools we have, such as New South Wales DPI's Twitter account and the quarterly newsletter All the Dirt. You can access these using the information on the screen now. And don't forget to subscribe to the webinars so that you receive a monthly invitation and you never miss out.